Okay. So last time we started actually seeing how the computer goes about simulating these dynamical systems, and we're going further into that today. From last time, we were focusing on this example of modeling bacterial clonal population dynamics. And so it sort of said that you have a basic homework assignment where in the first problem, you're basically going to replicate what we did from last time. And in the second problem, you add a death rate to it, which will actually be what we're going to see how to do this time. And then the second homework assignment so they're both kind of coupled together, is modeling the tank of a toilet as a balancing feedback loop. And so it'll be very similar to that. And so you kind of turn them in together as they're kind of these, well, not at the same assignment, but that's the reason why we've got two homework assignments due this upcoming Sunday. From last time, we sort of said that, we started this compound interest example, where in compound interest, you've got dollars that synchronously at certain compound events, all at one time, add a fraction of themselves to the balance for the next year. And so the way that would look is you start one year, and that year, you know how much interest you'll have available to spend the next year, but you don't get access to it until the next year. The next year, you now have that interest available. Each even little bit of interest generates more interest. That interest was available not for that current year, but for the next year. And then that next year, you got all of that interest that it's accumulated, and each one of it is accumulating more interest, again, not available for this year, but for the next year. And so there's kind of an example of compound interest over these synchronous compounding periods. And we contrasted that with a bacterial growth model where you've got a bacterium that individually, each bacterium waits on average W time units before it produces one whole second bacterium in parallel. And all these processes are going on in parallel and asynchronously. So they're not all synchronized together. We know how to synchronize, we know how to deal with the bank example, where all of the reproduction events happen at the same time and you get fractional reproduction. We don't know how to deal with this, where all the reproduction events happen out of sync, and at every reproduction event, you get a whole new individual that pops out. So we want to find a way to approximate one with the other. So the real time flow is you've got one bacteria becomes two, it waits for some period, let's say less than W, and then another bacteria, or that one bacteria becomes two again. That single bacteria then waits for another period, maybe less than W, to reproduce again. Maybe there's another period that's more than the average to reproduce again, and so on. And so this is sort of the way one bacterium is reproducing, and it's doing all of this while all of the other bacteria, including the new bacteria, are also reproducing. So that's what we're trying to approximate. So how do we get from there to there? And so as we talked about last time, we take this average behavior here, where you get one reproduction every W time units on average. And we are going to build a mathematical model of the average change in the population. And this is basically saying, if B is the number of bacteria, the rate of change of bacteria is the number of bacteria times 1 divided by their average waiting time until reproduction. So the thought here is that every one bacteria is adding one to, this is what we're sort of saying here, is every bacteria is adding one, that's the numerator, back into the population after waiting an average of W time units. And all of the B bacteria are doing that simultaneously. So the average trend is this differential equation. And so this is what we're trying to model inside our spreadsheet. And so our spreadsheet now has to integrate this over time. So we could try to use methods from, say, SOS 211 or a calculus class to solve this, but we want the spreadsheet to solve this. And so that's effectively what we're doing here. So the narrative that we can tell about the bacteria is that each bacteria produces 1 divided by W more bacteria per unit time. It's like the bacteria are constantly oozing out new bacteria at a rate, like a flow rate. That's why it looks like this spigot here, at at this, so you've adjusted the valve so it pours out at a particular rate. And so it's gradually filling up a bucket of new bacteria here. And if you waited for W time units, you'd fill up the whole bucket. But we are not going to wait for a whole W time units. We are going to wait for a very small amount of time that we call a time step, or DT is what I often will call it, but Sim and Insight Maker will call it time step. And so we say, if we know how many bacteria are available at the beginning of the time step, if they're all oozing out at this rate, then how many new bacteria are available at the end of the time step? And this is where that interest rate analogy comes into play. So it's like, this is how much is in the bank at the beginning of the compounding period. This is how much new bacteria is in the bank at the end of the compounding period, DT, where it's DT divided by W. That's the actual amount there. So that's the rate, that's the time, DT, times the flow rate, 1 divided by W. That gives me the amount at the end of this tiny compounding period. And we say that we want to choose the time step to be smaller or faster than the fastest thing happening in the system. So if it's one bacteria, the fastest thing happening in the system is that bacteria producing a new bacteria. So it does that every W time units. So we want DT to be far smaller than W. Another way to say that is we want DT divided by W to be nearly 0. So we want it to be really, really small. And by doing so, that helps ensure that, you know, like in our bank analogy, you're not allowed to use your bank, your interest until the end of the compounding period. Well, these new bacteria down here aren't allowed to start reproducing until the end of the DT. But we know that on average, these fractional bacteria immediately start producing their own fractional bacteria. So we need to be able to pull this fractional bacteria into the reproducing population as quickly as possible. And so that's the reason why we don't allow this fraction to get very large. We have to let this DT be pretty darn small, because that allows us to say, all right, how much is generated in the next DT? Let's move those over. Now let's see those generating, how much new stuff is generated. Bring those over and so on. So that's what we're doing to simulate these things. So to see that graphically, we've got, this is just like our compound interest, our bank balance of bacteria here, that's our stock. We've got each bacteria is oozing out at this rate. That rate that they're oozing out is flow. So then the interest being generated in our bank analogy is whatever the flow rate is times this tiny time interval, DT. So that's the generated interest. And then we iterate this. And so if we have one bacterium now, we'll have 1 plus DT over W bacteria in the start of the next compounding period. And then both of those will start generating new bacteria. And then these ones will be carried over until the next, and so on. And we want to make these compounding periods really, really small, because we know in the real system, then as you're adding to the average population, that average population positively feeds back on itself and starts reproducing. So as quickly as possible, we need this little bacteria up here to start reproducing. So it needs to very quickly get into the stock, and then they're reproduce. The ones they reproduce will end up having to get back into the stock as quickly as possible. That's why we need to make these DT time steps really small. And that allows us to approximate the smooth process that was in that differential equation. So, so we can take that, start with 1, we generate a little bit more, then each one of those a little bit more generates a little bit more. It's the same thing we did last time. We can zoom out, look at all these DTs, and again, if DT is very small, then we can smoothly approximate that exponential growth curve that we're expecting. But the downside is if we make DT really, really, really small, then the computer will end up, in order to simulate a millisecond of time, it'll have to go through like 1,000 or 1,000,000 calculations. And so the smaller you make DT, the more precise your predictions get in your simulation, but the more work the computer has to do. So as we'll see here in a few slides, there's a sort of a balance point where you find just the right size DT, where any smaller kind of doesn't give you any better results. but larger does give you worse results. And you kind of want to be around that level, maybe a little smaller than that for safety. So, and we'll see kind of examples of that. But ultimately, what we're doing here goes down to thinking about the definition of the derivative from calculus class, is that if we were plotting a function, in this case, the function would be stock. So if this is our function down here, stock, which I can call S of t for shorthand, if I'm plotting that function, so I'm just kind of drawing the same thing over time, if this curve, this is my S of t function, then I know that there's an instantaneous slope at every single point. So if I were to pick a point here, I could say, well, there's a slope at that particular point, and that is my derivative. And so what that basically tells me is that if I were to go down to this time, I could say, how fast is the population growing at that time? And that's what that instantaneous slope, that derivative tells me. It says that at this instant of time, you're producing 5 bacteria a second at the instant of time there. And so what that really means is if you were to go forward a very small amount of time, then if you follow along the yellow line, you'll stay very close to the red line. So the yellow line approximates the red line for a little bit. If you go too far away, then the yellow line diverges from the red line. So what we are doing is, in order for the computer, which doesn't know how to do the analytical math, the calculus, is we're basically approximating all of this by saying, well, we're going to simulate a point up here, and the slope of our original yellow line and this new blue dot, as long as that blue point is close enough to the yellow point, then the slope of the blue line is going to be close to the slope of the yellow line. And so if we want to approximate the yellow line, we can use the blue line for it, but we can only do that if our dt is really small. And that's what this bigger picture here is trying to communicate, is that what we're saying here is that as the, if we look at this triangle from the stock at time t to the stock at time t plus dt, which is what happens over here, we're approximating the stock as just being jumping up by whatever the flow was here times this small interval. And the actual stock, if we were to model the real function, is not going to be exactly at this point. But as long as we use the derivative, the flow, to predict a point very close to the original point, then this will be a good approximation of the function. So this is a so-called Euler's method for integration, is what we're doing here. So center back here. Yeah, let me clear that. Okay, so that's kind of where the math behind the small dt comes from. As dt becomes small, the approximation slope becomes equal to the derivative. The same way, if you think about the definition of a derivative as you take the little delta to 0, then the slope becomes the point definition of the derivative. So this is the formula, this is what we're trying to solve, but instead of using analytic methods, we use so-called numeric methods. And numeric methods basically turn calculus into algebra. And algebra is a pretty good approximation for calculus, so long as you're taking very, very small steps. Okay. So, so this is probably more abstract. I'm not going to expect you to be able to give a lecture on this, for the midterm, but I mainly am just trying to link this back to the tiny DTs that you're choosing in Vincem and InsightMaker are directly related to taking limits as delta, whatever you called it in your calculus classes, goes to 0 as you're defining what a derivative is. It's exactly the same. Okay, so what we did last time is we built a little spreadsheet that modeled this process where 1 bacteria becomes 2 every W time units. So the flow contribution is that each bacteria produces 1 divided by W new bacteria per unit time. And so we can calculate over a tiny dt how many new bacteria are being generated and let them start generating bacteria. We would like to add a death process to that, where it's the same idea. But now here, this is like at what rate does a bacteria add a new bacteria to the system? This is saying for every bacteria, at what rate do they remove a bacteria from the system? And so the math is going to be nearly identical, except instead of using a plus, we'll be using a minus. Instead of using an inflow, we'll be using an outflow. And so here, if I say their average time is 3 time units, so 3 hours, 3 minutes, whatever, then the contribution to death is 1 divided by 3. 1 bacteria goes away per 3 time units. It's the same as 1 bacteria comes into existence per W time units. So that's what we're sort of simulating there. So the total net flow from births and deaths per bacteria are 1 divided by W minus 1 divided by 3. This whole thing is per bacteria's contribution to the population. So if you take this and multiply it by the number of bacteria currently alive, then you find out the derivative, you find out the rate of change of the bacterial population at that instant of time. And that's what we're simulating inside the spreadsheet. So let's see what that looks like, and then we'll take some questions. And so this is the kind of cartoon of that. We've got a bacterial stock. It's got an inflow, which is the number of bacteria times 1 over W. It's got an outflow, which is the number of bacteria times 1/3, where 3 is the average lifetime. So that's our net flow is the inflow minus the outflows. So that's what we've all got here. We need to put that into a spreadsheet. And so this is kind of where we were last time. We said we had a DT, we pick a time step. We have our waiting time until births, 0.75. And now just to create a converter that might make it easier to read, I'm going to create a new variable called birth rate, which is the reciprocal of the waiting time until reproduction. It's just hard to say waiting time until reproduction over and over again. So rather than saying that, which is 0.75, I do 1 divided by 0.75, and that tells me the birth rate, which you can think of as like the rate at which a new bacteria is generated. So each bacterium generates 1 new bacterium per this time. So you can think of it as like bacteria per unit time per bacteria, I guess. So that's what I get this sort of birth rate there. So simulation time step, average time until reproduction, and then just for convenience, this birth rate, which is just the reciprocal of the average time until reproduction. That's what we had last time to start things off. And so now we're going to add the death in there as well, and then keep going with the spreadsheet. So this again is basically number 2 done for you of your homework. So you pay attention to this, you just have to reproduce it, and you've done number 2 of the homework. So any questions about this so far? Anything so far? I just want to get to this point here and pause before we add the deaths into it. Yeah. Any other number, yeah. Yeah, that was, thank you for asking that. And that, I'll be clear here, but if I here, I just kind of buried it here, 1 event every 3 time units. So it's like I went to the microbial biologist down the street, and I said, for this E. coli strain, how long do they live? And they'd say, well, each individual bacteria lives about 3 days. And so then that comes from that. So if they said for this other strain, then that might be 3 minutes, or it might be 5 minutes, or 13 minutes, or pi minutes, or whatever. Yeah. Any other questions? Questions online too. All right. Okay, so this, like I said, same stuff we did last time, but I added this little converter for convenience. Now let's add the deaths in. So this is like number 2 on your homework. So we're just going to add another parameter called average lifetime. So this also sort of answers that question. It's just a parameter. I'm calling it L for lifetime. I set it equal to 3, but it could be anything. It could be 15, 13, whatever. It's whatever the microbiologist tells me. And So, but for convenience, so that I don't have to say average lifetime all the time, just to kind of go along with my birth rate, I'm going to create a death rate, which is just 1 divided by the average lifetime. It's a redundant piece of information. You know, it doesn't, I don't need it. It just maybe makes the formulas cleaner downstream. So that's the reason why we've added it right there. So that's our death rate. So any questions about this before we get into the dynamic formulas? These are just the parameters and kind of their restructuring for convenience. Okay. All right, so now when we get down into the part where we start doing some dynamical simulation. And so I've got our reminders of these parameters up here. And so when we get to the toilet example, I'm just sort of saying this ahead of time. So a lot of times when we transition from the bacteria to the toilet, microbiomes aside, all of the parameters except for DT, go away. So a lot of times when people start the toilet one, they start with a W. And they say, what's my W for the toilet? The W is the waiting time until reproduction. So there is no W in the toilet. It has a totally new set of parameters. The only parameter you have in every single sim is DT, the time step. And the rest of these are up to for you to decide based on the problem. So then down here, with that in mind, the time column is going to be the same in every single simulation. It starts at time 0. And then the formulas are always going to be the time immediately before, plus whatever the DT cell is with $signs around it so that it stays put. And then that will create a time vector or a time series down this direction. And then that's our time evolution. So then I would start filling out the other columns. Stocks are the time is kind of like a stock. It has an initial condition, and all the other stocks have initial conditions. Everything else has a formula in its first row. So the initial condition for a stock, for this stock number of bacteria, we're going to say there's 1 bacteria at time 0. So that's what I wrote here. B0 is equal to 1. That's 1 bacteria at time 0. I just put 1 in that first cell. That's what that means right there. Then I go over to births. And this is what I mean about having that birth rate makes the formulas look a little prettier here, is that this is technically the formula that I want here is I want to say the rate of change of bacteria per unit time is equal to the number of bacteria times 1 divided by W. Well, I just took that 1 divided by W, I called that a birth rate, and that's what's right here. And then so this contribution to the rate of change due to the inflow is just going to be the number of bacteria times this birth rate per bacteria up here. And that will give me the total birth rate per population. So this is like birth rate per bacteria, and this is like birth rate per population. So it's just the number of bacteria times birth rate. Questions on that little part? That's just the inflow part. We need to get to the death part, but this is just the same stuff from last time, just with this birth rate being added in for convenience. So the formula is a little nicer looking. Questions online? All right, so then that's our inflow. So then our outflow. So in the rate of change formula that we're end up simulating here, we have that inflow that I put as 3 dots now, minus the outflow, which is the same formula as before, as the inflow, but now instead of using W, we're using L. So we're saying that you subtract away bacteria, 1 per bacteria every lifetime of a bacteria on average, and you scale that by the number of bacteria. Well, that's all I have here for my deaths flow is I'm not going to worry about the minus. That'll come into play down here. It's the number of bacteria times the death rate per bacteria. And that will give me the death rate for the whole population. So questions about that? Okay. So then I just need to fill out formulas. I only have 1 more formula to fill out because these 2 automatically fill down. This one fills down. So all I need here is the stock update formula. And all the stock update formulas across all your systems are going to look very similar to this. They're always going to be the previous stock value plus DT times all of the inflows added together minus all of the outflows. So minus outflow, minus outflow, minus outflow, or minus parentheses outflow plus outflow, or whatever, how you like really to write it. So in this case, we have one inflow, which is births, one outflow, which is deaths, and we multiply that by dt, and we add it, and that, so you can kind of see the correspondence down here to this formula. If you were to sort of forget about the dt and just focus on the things that are in the parentheses, the things that are in the parentheses are this differential equation that we're trying to solve. We're putting it into the spreadsheet and letting it solve this for us. So the spreadsheet's number of bacteria will be the solution B. It'll tell us what B is over time, the number of bacteria is over time. So questions about this stock update formula. Again, this formula is going to be the same in the toilet example, in this example, in any example you have. It's always the number of, it'll be this exact same formula, but inside the parentheses, you might have more inflows, you might have more outflows, but it'll always be inflow plus inflow plus inflow, minus outflow, minus outflow, minus outflow. In this case, we just have one inflow and one outflow. Does that make sense? Questions online? Okay, so let's see after we fill down what happens. So I took my time, the second row of time, filled it down. I took the second row number of bacteria, filled it down. I took the first row of the flows, filled them down. And after I filled everything down, if you fill them down one by one, you might get some numerical errors or whatever. But once you fill them all down, then they'll start, connecting together like Legos, and it'll finish up. And if I plot time against number of bacteria, I get this exponential growth curve. And this exponential growth curve, this is the numerical solution as opposed to the analytical solution. It's the solution the spreadsheet found instead of us doing the math to this differential equation. And we know if I was to manually do this by hand, that my solution would be proportional to an exponential raised to the t times 1 over w minus 1 over l. And it turns out that that's exactly what this is right here. It's a growing exponential. So this is exactly what we expected. Now, if I were to go and show you the one from last time when we didn't have death, it would have the same shape, but the one without death would get to a much higher level. And does that make sense? So why would the one without death look exactly the same, but go to a higher number of bacteria at the same time? Yeah. That sounds great. So for those who didn't hear that, because we've added in an outflow process, then we're seeing the net effect of bacteria being added and lost. So the net effect is bacteria being added, and that's because, if you look at these parameters, W.75, L of 3, well, you wait a shorter time for new bacteria than you do for old bacteria to go away. So long as W is smaller than L, then this thing will grow. If I were to go into this spreadsheet and make W equal to 4, then this thing would, if I started with 140 bacteria, it would decay down to 0. If I started with 1 bacteria, it would decay to fractions of a bacteria, so it would go down. So it's growing because the lifetime of a bacteria is longer than the time it waits to have new bacteria. And so that's why we have this exponential growth. Okay, so any questions? Yeah. Oh, well, so like in the homework, I will say that we want to simulate it for 5 time units. And so that's a great question, is that you fill this down until you have enough rows for 5 data points. So that's tricky because also in the homework, in part 3 of the homework, I have you experiment with different DT values. And so if you change your DT, if you make your DT smaller, then you're going to need to add rows to get the total time up to 5. If you make your dt larger, you're going to have to subtract rows away to keep your dt equal to 5. So as you change your dt, you change the number of rows in order to get the total time. And so in a simulation application, you'll normally either simulate until some event happens. And so you might just need to sort of keep dragging down and seeing what it looks like until an event you're looking for happens. Or somebody will say ahead of time that we're not only interested in the behavior over the next 10 years. And so then you only simulate out the 10. So in the homework, I say 5. So that's how you know. Other questions? And I also saw the comments online, no outflow. That was an answer to the earlier question. So that's right, no outflow. Okay, great. So then the last thing here, and again, I'm basically doing that homework for you, which is why I don't feel bad about giving you a second homework assignment due Sunday. But the third part of that homework asks you to compare different dt values. And so this is, when I did this is my dt of 0.01, 0.001, and 1. And so if I look across here, they all have the same general shapes, but one thing we notice is the one with a very high dt, you can kind of see a corner here, like right here is a corner, right here is a corner, right here is a corner, right here is a corner. In fact, it's every dt. You can, if you look really closely, you go 0 to 1, and there's a slight change in slope. 1 to 2, slight change in slope. 2 to 3, and then at 3, slight change in slope. And then it's the strongest here. At 4, there's a strong change in slope as it goes to 5. You're seeing there this approximation of a smooth function by a bunch of lines that each have that kind of flow slope. So it's the flow at each point. It just takes that. And so you're really seeing it here because there's large numbers, the dt is very large. You're also seeing it only takes 0 and then 5 rows. So it takes the initial row and then 5 more rows, so 6 rows total to get this plot. But it takes a lot more than that to get these plots. So that goes to that point that we just made. The other thing to notice is that a dt of 0.01, after 5 time units, we have 140 bacteria, a little more than 140. At dt of 0.001, after 5, so this is smaller, after 5 time units, we have roughly the same plot. It's a little bit higher, but it's roughly the same. But at dt of 1, where it's very, very large, we only have 30 bacteria after 5 time units. And so that goes to show that if you make your dt too large, you miss out on a bunch of events that you're trying to approximate a count of. So this is sort of saying that this one here, we're sort of saying that we take the population at time 0 and we see how quickly they're reproducing at that instant. And we assume that that population birth rate is going to be the same all the way to 1. Well, that's crazy because there's so many reproduction events during that 0 to 1 that those bacteria don't get a chance to start reproducing until 1. So all of that delayed reproduction is lost reproduction in the model. So that's why this model is undercounting the number of bacteria, because it's undercounting the number of reproduction events. And so we find that if we make our dt smaller and smaller, eventually we find some point, say in between dt of 0.01 and 0.001, where the graph pretty much settles down. This graph looks a little more jagged than this graph, but overall, if we were to put these on top of each other, they all hit the same points. So that tells me that I could simulate even more rows, but eventually I'm going to have so many rows that every time I open my Excel spreadsheet, it's going to take a little bit of time to generate all those numbers because it has to do all those calculations. So it doesn't benefit me by having Excel take the extra time when in the end, the plot I get looks the same as the plot I get with this one up here. So does that make sense, what I mean by the DT? Yeah.
So when you're modeling, would you like try to strike somewhere in the middle of those two, or you opt for the second?
Well, it kind of depends on how conservative you are and how much you knew about the sort of fastest, what we talk about is how well behaved the system is. So once you do this enough, when you look at the flow formulas, you can start recognizing there's families of different flow formulas, some of them that have a tendency to create a lot of very fine timescale behavior, and some of them which are generally pretty smooth. So in the technical terms, we talk about stiff differential equations and non-stiff and things like that. So these are kind of advanced things, but eventually, so basically, the simple answer is it depends. But normally it's a sort of a process of making your time difference smaller and smaller and smaller until you get something settled down. And then when you look at the behavior, check with any other knowledge you have, like go to the microbiologist and say, does this make any sense to you? And if they say, yeah, actually that's similar to a growth curve we see in the lab, and in fact, it seems to hit the right numbers at the right times, then you've built confidence in your model. Now, if it's never settling down, there's a step that goes beyond the scope of this class where you actually have to change your integration method. And so when you go into Insight Maker and Vensim, right next to the point where it says time step, which is the DT, there's another thing next to it that'll say like integration method. It always defaults to Euler. And that's what we're going to use for this whole class. But if you get to more advanced methods, then you actually find the point where you need to click on that box and change to a different way of integrating. And this is a little bit like, if you remember back to maybe when you're first learning how to do Riemann integrals and things like that, how you could do like rectangular approximations and trapezoidal approximations. And I don't know if anybody remembers doing all of those different ways you could formulate the integral. Well, though all of those ideas apply to how you can go into a spreadsheet program and approximate smooth curves with lines. And by choosing different ways to do it, then you can actually deal with some difficult systems that you can't just kind of zoom in on and suddenly everything's okay. So that's getting a little bit out of this class scope, but it is possible to do, and it's not super exotic. It's just not like it's a little exotic for 212.
So the smoothness of the curve is actually more important than the delta of the final.
What do you mean by the delta of the final endpoints? Mm-hmm. Right, and well, it kind of depends on where you care about predicting, and so that's the other thing I kind of didn't say, but I'm glad you mentioned. I should have brought that. If we really needed an initial condition here, and we really needed to simulate behavior way over there, and we determined that we needed a very small time step, in order for us to get the predictions accurate, like if we didn't care about the relative shape, but we care about the absolute shape, then we might also need to crank the DT down because we're just integrating error. And so here, after 5 time units, there's not much error, but if I would have kept this thing going after 10 time units, 20 time units, and so on, then these two would start seeing a lot of daylight between them. And so, but this one and another order of magnitude down, DT 0.0001, then maybe those two all the way to 20 would look pretty much like each other. So it depends on how far out you want to go, and it depends ultimately on how ugly the thing you're simulating is. Something that grows smoothly like this is not a problem, but there's a bunch of other systems that as you zoom in, it's like got this fractal behavior, like kind of like lightning. If you ever zoom in on lightning, you keep seeing lightning. You never ever see a straight line. And so if you generate a dynamical process that produces lightning, that takes a much more sophisticated integration tool, because at no point can it just say, well, I'm just going to approximate this as whatever the derivative is, and then a straight line after that. And so there are tools that do that. They're just outside of the scope of this class. All right, great questions. Any other questions? This is sort of the most abstract thing about DT, but it's the thing that you actually will use, like you're in your Vensim and Insight Maker. You can forget about all the spreadsheet stuff as we get further on in this class, but you're going to keep using this DT stuff, because every time you build a model in Vensim or Insight Maker, you're going to have to choose a time step. And you're basically going to be doing this. You run a little pilot study with one time step, Then you try a time step a little bit smaller than that and see if you get any different results. And that'll tell you if you've chosen the right time step. Okay, great. All right, so like I said, finding the right T. Too large, inaccurate simulation. Too small, the sim takes way too long. So I think we're good. All right, so we in VinSim and Insight Maker will be drawing diagrams that look more like this. We can see our stocks, we can see our converters, we can see our flows. The DT is hidden. It's actually buried in the software settings somewhere, so it's not actually reported anywhere on the diagram because it doesn't relate. This relates to sort of the fundamental structure of the system, whereas DT relates to how we're approximating the system, and that's why it doesn't really show up on the diagram. But overall, this diagram is identical to this mathematical expression, the integral of the flow. It's also identical to this mathematical expression, the derivative of the flow. So if you ever see this, or this, or this, you can translate to the other one. So, oftentimes when we model systems, depending on the people involved, sometimes they'll write some of these, sometimes they'll write these, and sometimes they write these. And a good modeler should, even if they aren't necessarily educated in the methods of the other modelers, they should be able to translate so that if there's results that come out from the mathematical modelers who purely write this way, you should be able to reproduce those results numerically in your simulation tool. And so you'll be able to translate from their diagram into yours, and then maybe you'll be able to offer some complementary results because you'll be able to show how the system behaves over all time rather than maybe just the time at infinity or something like that. So these are all equivalent, and that's what links this back to calculus. And in our bacterial case, this spreadsheet that we built in this lecture here, this is how I would draw it out inside VinSim. And so I can have a parameter, average time to reproduction. I can have a that itself has a negative link to birth rate because it's 1 over that. And then birth rate has a positive link to the birth flow, and I can tell the flow because it's got this solid line. I can tell that the deaths is an outflow because it's like a solid line. I can tell the number of bacteria is related to births because it's got this positive link. More bacteria, bigger flow. This one's got a positive link. More bacteria, more deaths. Same thing here. Average lifetime is the ultimate parameter I asked my expert for. 1 over that, that's the reason why there's a minus there, goes into death rate. And if more death rate goes to more deaths. And so that kind of combines the kind of causal loop diagram with the stock and flow diagram. And the result is identical to this formula that's down here, this expression, which we then can reproduce numerically here. And VinSim, you'll draw this, and whenever you hit play behind the scenes, it'll build this. And the graphs you get out, which will be like these little graphs here, will approximate this. So that's the big picture. So any questions about that before we see the toilet examples? Yeah, no. Questions online? Okay. All right, so that basically, if you were to go back and watch this lecture or go over these slides, that was pretty much a visual answer key to assignment D1. So it's just your practice on building that population model. After you do that, then you've got assignment D2 where you're going to have you do a little bit more on your own, but I'm still going to help you quite a bit here in these next couple of slides. So the goal of assignment D2, assignment D1 was about growth. So it's about a reinforcing loop. Assignment D2 is about a balancing loop. And a simple balancing loop is the water in the back of a toilet tank. So I'll show you that here in a second. So assume that we've got a water level is initially, the tank is empty, so it's 0 centimeters high. We're trying to fill the water up to 15 centimeters in the back of the tank and stop. And we've bought a flow regulator at your local hardware store that adjusts the flow so that it's strongest when the tank is empty and weakest as the tank gets up to the very top. And so somebody's designed it so that it produces a centimeter per second inflow equal to the difference between the current water level and the target. So this is the valve here, this is the target, and this is the actual level. So, so you're going to build a spreadsheet that will simulate what the water level looks like over time. You're going to plot the water level as it changes over time, and then choose a sufficiently solved DT to make sure that your spreadsheet's a good approximation. Make sure you produce a nice plot with titles and units on the axes, and show at least 5 seconds of this filling process. And then also I want you to upload both your spreadsheet as well as a Word doc where the plot is embedded within the Word doc as it would be if you were putting together a report. And then, so that's what you'll do for part 1 of it. And then after you do all of that, hopefully you'll recognize this is a balancing loop. And if not, you'll see it in just a second. And so then I want you to draw a CLD in VinSim or Insight Maker to submit to part 2. And then if you like, the extra credit for this one is to add a continuous leak to it. So imagine that the toilet is leaking into the bowl, which ultimately leaks out. And so how is that going to change the dynamics of the water that's in the back of the tank? And so we get to see that there. So let's see that. This is kind of like I said, it's a basic balancing feedback loop. If you don't quite, so this is an example we had earlier. This is effectively the toilet tank, but this example is, it's more of an outside than an inside example here that we're looking at the bucket and we're using information from the current water level to decide the flow of water. And so the goal is the target water level at the top. The actual water level is down here, and the action is this flow here. So if we look at the toilet tank in particular, then here's our toilet tank here. And we've got the water level. So the level that's actually in the tank back here, that's down here, water level. The flow, that's what's coming in through the valve here. So it's bringing water in through the outside into the tank. That's here. And the target, that's the level at the top, that this little auto leveling assembly. So this little bobber here, when it gets appropriately high, as this bobber is getting more and more horizontal, the flow into the tank is getting less and less. And so that's what sets up this little valve here. So that's our balancing feedback loop of the toilet tank. And so ultimately, this is, what this up here, this is the equation that describes the back of a toilet tank after you flush it. So we have our flow expression, which comes from the manufacturer of the valve. And this is the rate of change of the water level. So we're saying the rate of change of the water level is just 15 minus the current water level. So when it's all the way up to 15, there shouldn't be any rate of change. When it's all the way down to 0, it should be bringing water in at 15 centimeters a second. And so we put that in our diagram here. The formula for the flow is 15 minus L. The stock is L, and those two iterate on each other. And so the target, I've sort of embedded it in the formula, but 15 is the target. So that's how this is a balancing loop. So any questions about how the toilet tank is a balancing loop? It's constantly trying to bring the water back into balance. So it's like 15 is on one side and the water level's on the other side, and it's constantly trying to get them balanced again so that the water level is back to 15. Okay. So you're gonna have to put that into a spreadsheet in order to simulate it. So this is our generic stock and flow spreadsheet. And so you could start with a spreadsheet that looks like this, where you've got time down one column, you've got a stock column. In this case, we only have one stock, the water level, a flow column. In this case, we only have one flow, the inflow of water going into it, although the outflow is in the bonus. And then you possibly could have converters if you wanted to. So in this case, a converter might be the tank gap. So the amount, the difference between the water level and the target, that could be your converter. And then that converter could then end up setting your flow. But you don't have to do it that way. So, so this is how you might do it. So again, this is kind of doing a lot of this kind of already for you here is I've got my DT. There's not a W in this. It's not the bacterial example. There's just a target 15. So I use that as my parameter here. And so you build this spreadsheet. So this is what you're going to be doing on assignment D2, is you can start, if you want, with this spreadsheet, or you can embellish on this, and that's totally fine too. And you have to fill in the formulas for time. This is the formula for the stock, so that's already done for you if you stick with this one. Well, then you have to fill in the formula for the flow and the initial condition for the water level. And it would be great if your formula for the flow made use of the target here, and that would allow you to change the target and see how it changes things. Remember, ultimately, you're simulating this, and so you kind of see what the flow equation is supposed to be here, 15 minus L. You effectively need to put 15 minus L into that inflow. So this is what you'll basically be doing on assignment D2. So this is a big hint. So any questions about this, the layout of this balancing feedback loop as a spreadsheet? Questions online? All right, so basically, this is lecture D2. We've got lecture D3 and D4. D4 is the lecture where we go over Moorcroft's introduction to stock and flow. And so make sure you read that for a week from today. No, a week from, yeah, this is D3. Yeah, a week from today. So then also try to, again, think about your final project teams. There is, I think it's shortly after the midterm, there's a Canvas assignment where you have to submit your team member names. Every member of the team submits who they think is in their team so that I can go through and make sure everybody agrees. And then once everybody agrees, I'll create groups. And then every other final project deliverable will be a group assignment. Only one person has to upload and then they all get it. If there is a spreadsheet online, if you go to the final project module, then you can access that spreadsheet and you can put in if you're looking for a group member or looking to join a group, and that'll hopefully help people find each other, or feel free to use Slack or the discussion boards and so on to reach out. We will start using Vim and Insight Maker to start building these. So this is our last kind of spreadsheet based assignment. So in D3, we're going to reproduce these things in Vim and Insight Maker so that we know how to build them in those tools. And we'll see how much easier it is using those tools. So for basically the rest of the week, there's assignment D1 that we talked about. There's today's assignment D2. There's a muddiest point due Sunday, and that's about it. So for the rest of, well then, all right, so the midterm is not that far away. So we're going to have, finish up unit D. That's, again, this is D2, there'll be D3 and D4. Then I guess Thursday of next week will be the midterm review, which I'm calling lecture DE. And then the week after that will be the two-stage exam. So I guess if I'm doing the math right, Tuesday will be stage 1 and Thursday will be stage 2. You can come to class for one or both of those, but you don't have to. Stage 1 will be timed. I'll give you 90 minutes. So if you come to class, you have to stay a little bit longer than class, but you can take it really anytime that day. And I might give you a little bit more time. I'll have to look and see. I think I currently have it scheduled so that you actually have a little bit more time. Once you start it, you have to finish it within 90 minutes. It's closed book, closed notes, closed classmates. You do it totally individually. You will get one sheet of double-sided notes if you wanted, a crib sheet. Then stage 2 will be 2 days later, and it's group. So it's open book, open note. You can collaborate with classmates and you'll have the entire availability window to work on it. So it's not time. And your midterm will be 80% of stage 1 and then 20% of stage 2, and add those weighted scores together and you get your midterm score. There are resources available, including midterms from previous semesters and practice problems and so on in the unit DE midterm module. So that's all I've got. Any questions about that? And basically for the rest of the time in the class, you can either go, or if you'd like to start working on assignment D1 and D2 in class and with each other or with me around, then you're welcome to do that. Otherwise, if you'd rather just do it at home and get out of here a little bit early, then that's fine too. But so any questions about this before I put up the attendance exercise? Yeah. Stage 1 is lockdown browser. For simplicity, if you come in person, you can use these computers and you'll use lockdown on these computers, or you can bring your own laptop. But yeah, I mean, it seems a little silly, but it just, rather than me having to deal with like passwords and things like that, then you can just come to class. And I mean, ultimately, when you're doing all the lockdown stuff, I mean, I will see that you're in the classroom. And so you're not going to have to like, like show me where you are or anything like that. So it can be, I'm not one of those people that just like looks to see what lockdown automatically flagged and then kicks someone out of the course. So if, I'll review things as necessary, and so I'll know who was in the class, and I'll know if it's a classroom behind you, and I'll be more flexible about it. Any other questions? Questions online? Is that okay? All right, in that case, then put the attendance exercise up here. Let me get my mouse back. Maybe. Left, there it is, okay. So I'll put in the chat the link. And the question for today is, what type of feedback loop is a toilet tank? Is it a reinforcing or a balancing? And like I said, that's all I got for you. So if you want to hang around and work on your assignments, that's totally fine. I'll be here until 5:45. Otherwise, we'll see you Thursday. And for those of you online, I will probably end the recording for sure. But if any of you wants to hang online to get help from me, that's fine. Otherwise, I'll see you Thursday. So if you have any questions, feel free to raise them. Okay. All right, great. Have a good night. Have a good night.